Hello. So we're in chapter 3. We're talking about Newton's first law of motion, the law of inertia. So forces cause changes in motion. In order to have a change in motion, you have to have a non-zero net force being applied. An example of this is the game of soccer, or football if you're not from the United States. A ball at rest in the middle of a flat field is in equilibrium. No net force acts on it, and it continues to not have any change in motion as long as a non-zero net force continues being applied to it or continues not being applied to it. So the point is if you apply a non-zero net force to that ball, you can act to accelerate that ball. We bring up Aristotle in this section. So Aristotle was the foremost Greek scientist, and he studied motion. He divided motion into two types of motion. One of them was natural motion, and the other was violent motion. So we have natural motion and violent motion according to Aristotle. So he described natural motion on Earth, and it was thought to be either straight up or straight down. Objects seek their natural resting places. In other words, boulders rest on the ground, smoke rests high in the air like the clouds, heavy things fall, light things rise. Circular motion was natural for the heavens. This is how he reconciled the motion of the planets, because in Aristotle's time, and Aristotle himself believed that the Earth was the center of the universe. And so in order to reconcile the apparent motions of the planets, they had to define their natural motion as being circular, because you could see them doing figure eights or other different circular type motions in the sky relative to our vantage point here on Earth. These motions were considered natural and not caused by forces. So violent motion is imposed motion. Notice I have a picture of a rocket here. This is violating natural motion. According to Aristotle, natural motion, anything heavy, anything hard, should be resting on the ground. And so if something's not resting on the ground, then it must have had some type of motion imposed on it. In other words, violent motion. And that's what he called it, imposed motion. So violent motion, according to Aristotle, was the result of forces that pushed or pulled. An important thing about defining violent motion is that it had an external cause, if you define the thing as part of its own system. Violent motion was imparted to objects, and objects in their natural resting places could not move by themselves. Boulders don't move without cause. So it was commonly thought for nearly 2,000 years that a force was responsible for an object moving against its nature. The state of objects is one of rest unless they're being pushed or pulled or moving toward their natural resting place. Most thinkers before the 1500s considered it obvious that Earth must be in its natural resting place. They couldn't imagine that there was a large enough force to move the Earth. And so they thought that the Earth didn't move. And so if the Earth didn't move, it must therefore be at the center of the universe. And you can kind of follow their logic, at least. If you think about a rock, it's hard to move. You think of a bigger rock, it's harder to move. You think of a rock the size of a mountain, as far as we know, it's impossible to move. And so imagine something the size of, all the mountains on Earth, or literally the Earth. So according to Aristotle, what were the two types of motion? And there was two types we just talked about. One was natural and the other was violent. So along comes Copernicus. Copernicus and the moving Earth. So Copernicus reasoned that the simplest way to interpret astronomical observations was to assume that Earth and the other planets must be moving around the sun. This is probably an Occam's razor type event where the solution that had the least complexity must be one worth exploring. And as Copernicus explored this idea that the sun is the center of the visible universe, being the solar system at the time, he reasoned that the Earth and all the other planets that appear to be doing these weird circular orbits that don't really make any sense, if we just say that they're all orbiting the sun and everything just works out. The math works out and everything's moving in orbits. Unfortunately, at the time, Copernicus reasoned that they're moving in perfectly circular orbits. We know that that's not necessarily true. Most, if not everything we know of, moves in an elliptical orbit or a non-perfect circular orbit. But, he's close enough. So Copernicus and the moving Earth again, the astronomer Nicholas Copernicus formulated the theory about the moving Earth, and this idea was extremely controversial at the time. People preferred to believe that the Earth was the center of the universe, and there was a lot of theologies and ideologies at the time that required the earth to be at the center of the universe. They believed in order to be special, they had to be at the center of the universe. And so there was a lot of issues with speaking against what the prevailing religions at the time believed. And so this was a very dangerous game that Copernicus was playing, recognizing the obvious fact that the earth was orbiting around the sun, because religions at the time didn't want to believe that anything but the earth was the center of the universe. That was very difficult. And so that was risky, because a lot of times governments would unite with religions, and if you didn't go with the prevailing religion, or at least the government that the religion that your government endorsed, then you were in danger. So there's a lot of potential political backlash, and this is why Copernicus released some of these ideas in private. All right, and so what did Copernicus state about Earth's motion? He stated that Earth was orbiting the sun. So Galileo also argued something very important about friction and about motion. So Galileo argued that only when friction is present, as it usually is a force needed to keep an object moving. And we'll talk about his experiment in just a minute. So he was the foremost scientist in late Renaissance Italy. He was very outspoken in his support of Copernicus. So Galileo was going further with some of Copernicus's ideas. One of Galileo's greatest contributions to physics was demonstrating the notion that a force is necessary to keep an object moving. So friction. Friction is the name of force that acts between materials that touch as they move past each other. Friction is caused by irregularities in the surface of objects that are touching. I like to think of this, and I've kind of explained this to my students. You look at a smooth table, and that table looks smooth. But if you imagine zooming in far enough with a microscope, you'd see that surface was very full of irregularities. And if you imagine kind of putting your fingertips together and kind of moving your hands against each other, your fingertips kind of provide a resistive force against your other fingers, preventing that motion. And you can imagine an object sitting on top of the table. Even though the table's smooth, and even though you might have a smooth object, as you slide the objects against each other, there's going to be some irregularities, some at least atoms rubbing against each other. And those atoms bumping against each other are going to create a force, a resistive force. If there was no friction, a moving object would never need a force to remain in motion. In other words, if you rolled a ball on a frictionless surface, it would continue rolling indefinitely. So he tested his idea by rolling balls along plane surfaces tilted at different angles. And he noted that a ball rolling down an inclined plane speeds up, which is obvious. A ball rolling up an inclined plane in a direction opposed by gravity, of course, slows down. A ball rolling on a smooth horizontal plane had almost constant velocity. And so here's a diagram. Let me just scroll down. Got these from the textbook. So in this situation, we have speed increasing because gravity is accelerating the object, or at least force due to gravity is accelerating the object. And then B is force due to gravity is decelerating the object. And then C, there shouldn't be a change in speed. Of course, as friction is present, we see things slowing down. So in his experiment, he has two inclined planes. They're facing each other, kind of like at a skate park. At a skate park, the skateboarder can go down one slope, and by pumping their legs, they can not lose too much kinetic energy. But with these ramps that Galileo used, he was able to see that the higher up he started on one plane, the higher up he ended up on the opposing plane. And as he perfected the surface of the ramp and reduced the irregularities in the ramp, he was able to show that if you could theoretically approach zero friction, you could theoretically approach that final position. And that final position was always proportional to the initial position. So this combination of ideas led to the conclusion that this is all due to friction. Friction is the force that's taking away from the motion of the ball. So his final postulate was that if he removed the final ramp and there was zero friction, the ball would continue rolling indefinitely. All right, so he stated that the tendency of a moving object to keep moving is natural, and that every material object resists change to its state of motion. So Galileo's adding to Copernicus's postulate in saying that an object that is in motion, it's natural for it to continue keeping that motion indefinitely unless another force acts on it. And so this other force was deemed to be friction. So this property of an object or a body to resist changes in its state of motion, being stationary or in motion, is what we call inertia. And this happens to be Newton's first law. All right, so that's that. An example of this is the old experiment with a tablecloth. You've probably seen people doing this. You pull the tablecloth. The objects on the table all have inertia, and so they're resisting change in motion. And so if you whip the tablecloth out from under them, they don't have enough time to be accelerated to change their state of motion, and so they remain motionless. Here's a few cartoons that kind of also illustrate this idea. You might imagine yourself, hopefully you didn't do this, I'm pretty sure I remember pulling my little brother on a wagon and having something similar to this happen. I know he didn't get hurt. So a body at rest tends to stay at rest. And so if you're not holding on very well and someone moves a wagon out from under you, you're going to stay in your current state of motion, which is at rest. And that, like in this picture, that dog jerks forward and the boy just ends up on the ground. Similarly, if an object is already in motion, then it's going to tend to stay at motion. And if you try to stop it in the manner of this person, that truck is going to have a lot of inertia because it has a lot of mass, and you have a lot less mass, so don't try this. Is it correct to say that the reason an object resists change and persists in its state of motion is that it has inertia? Ask yourself that, and the answer is yes. So as we just stated, Newton's first law of motion is the law of inertia. This is Newton's first law, inertia. An object at rest tends to stay at rest, an object in motion tends to stay in motion. And I decided to pull this picture of drifting vehicles because it looked cool. Okay, so if you have an empty can, we don't really eat out of cans as often as when I was little, but imagine you have a can that's empty versus a can that's filled with sand or just a can that's full of food. You kick that can that's full of food, it has much more likelihood to hurt your foot, and the reason is it has more inertia. So it's going to take more to get that can accelerated to the same speed as your foot, whereas an empty can is very easy to accelerate. All right. So we have a pillow and a battery. The pillow and the battery have very different masses, they have very different inertias. So the pillow has a larger volume, but still has a smaller mass. And so if you were to kick that car battery or kick that pillow, the pillow would be much easier to kick. I do not recommend kicking a car battery, especially the fact that it has acid in it. We don't want to spill acid everywhere, and you'd probably break your foot because it has lead in it as well. It's pretty dense. So something interesting. I gave this example in class. I told everyone to hold a pencil and then their textbook in each hand and try to see how fast you can move that pencil, how fast you can wiggle that pencil in the air. And then that same speed that you could wiggle that pencil, I asked everyone to try to wiggle the textbook that fast, right? Wiggle a dense object. If you're watching this from home, find something that's heavy and try to wiggle it as rapidly as you could wiggle something that's very light or very low in mass or very low in inertia. And it's going to be much harder to move the object that's high in mass. Same thing would happen in space as it is on Earth. This isn't because of gravity. This is just because of inertia. And I think this is one of the best ways to really understand inertia. All right, so I think that's all the stuff I wanted to pretty much cover. Let me see if anything jumps out at me. It's not like you, at that high speed, are having issues flipping a coin and catching that coin in your hand. That coin's not going to fly to the front of the airplane or to the back of the airplane at 600 miles an hour because you and the coin are both moving at the same rate. Since you both have the same rate of speed, you're flipping that coin as though you are motionless. So that's inertia in action. All right. So thanks for watching the presentation. If you have any questions, leave a comment or just ask me. Thanks for watching. Don't forget to subscribe.